Students, I know that statistics can be really confusing, so I thought I would just throw this together so that you can review it over and over, or for the first time if you missed class about statistics, just so we're all on the same page, because I know Bio 130 tends to move really fast. So let's just do a new hypothetical situation. So we've been doing the burying beetles, but we're going to do this situation. So let's say we have a puzzling observation. My son, he pulled an all-nighter studying for a test. He scored a 52%. But on a different test in the same class, my son studied, but then he gave up and he went to bed at 10 p.m., got a full night's rest, and he got an 86%. So that was kind of weird. So let's say, based on that, I ask my causal question, why? Why did he do better on the second test than the first test? Let's say that my hypothesis is that sleep is beneficial to student retention of learning, that sleep is the causal factor for making you learn better. All right, so let's say I have that. And let's look at the null hypothesis. Our null scientific hypothesis would be that sleep has no effect on student retention of learning. My hypothesis is bogus, doesn't matter, right? All right, so let's say I set up an experiment and I take two groups of students in my introductory biology class and I do the unit of instruction, and then I invite both students to a study session from 5 to 7 at night, and then I divide them into two treatment conditions, a low sleep treatment and a high sleep treatment. My low sleep treatment, I make them watch Netflix all evening and they go to bed at 1 a.m. My high sleep treatment, I send them home at 7, tell them to get a snack, brush your teeth, go to bed. And they both have to wake up at 7 a.m. The test begins at 8 a.m. Okay, so there's my somewhat controlled test. And let's say I get this as my outcome. So the low sleep group scores like a 75%, the high sleep group scores an 81%. So is that different enough for me to say, gosh, that's weird, I think sleep is doing something? Or is this just in the range of normal variation, right? How uncertain are we? So that's where statistics come in. All right, so let's decide how far off from our expectations do we need to be in order to conclude that this really isn't just due to random noise or chance. And so let's do a hypothetical just to simplify in a situation where we know what the odds should be. So let's say I have this coin and I'm wondering if this coin is magical. Someone's told me that it's rigged. So I go and I flip it 100 times and I get 81 heads and 19 tails. Well, that seems pretty unreal, right? I get 81 heads, 19 tails. Is it a rigged coin? Okay, so let's look at let's back up. Our hypothesis is that the coin is rigged. But what's our null hypothesis? Our null hypothesis should be, no, the coin's not rigged. It's really a fair coin, right? So any difference from 50-50 is just noise. So that's our hypothesis, the coin is rigged. Our null hypothesis, the coin is not rigged. Okay, so then we've got to figure out, how do we figure this out? Well, we have to come up with some kind of weirdness score. How far off is our flips from what we were expecting? And so I introduced in class this measure of weirdness. A measure of weirdness is called a statistic. And in this particular case, when we have known values and distributions, we call it a chi-square. So chi is that Greek symbol. And basically we take, what we observed, we got 81 and 19, versus what we expected, and we figure out how far away it is by subtracting them. We square it right here just because we want it to be a positive number, and then we divide it in this case because we want a percentage. Whatever. We had a much more simple equation in class, and that's fine too. But we're measuring how far off we are. So then, how do we decide how far off is too far off? Well, we build this. This is called a sampling distribution. So I want to really have you stare at this for a minute. This is saying, what if I took this same coin and I flipped it 100 times and I did that 10,000 times? And each time I plugged what I got into my chi-square formula and I got a number. So along the x-axis is the value of the chi-squared. And along the y-axis is how often I get a value that's that weird. So you'll notice, and this should actually not go to the 0 right here, it's not a very good drawing, but you'll notice that most of our values, the highest probability values, are just where we're a little bit off. 1 off, 2 off, 3 off, 4 off, 5 off, maybe even 10 off from our 50-50. But as we get more and more off from that 50-50, it gets less and less probable. Okay, so the x-axis is the value of the weirdness score, of the chi-squared. The probability is actually the area under the curve. So there's high probability here, and then it gets lower and lower probability. And so we say ahead of time, before we run the test, we say, how weird does it have to be for me to say, I think the coin is rigged? And so I arbitrarily choose that if it's 5% or less in its likelihood of happening by chance, which is this blue area under the curve, that's 5% of the total area. If it's 5% or less, I'm going to say, that could be just random noise, but it seems so weird. I'm going to say, no, the coin is rigged. Okay, and so to figure out where, that's your alpha value. That's the value you set ahead of time of how much chance you're willing to take that you're wrong. And then we say, okay, if the chi-squared value falls anywhere on the left side of my cutoff line, then we're going to fail to reject the null. We're going to say, that happens a lot by chance alone. And so I don't think anything's going on. I don't think the coin is rigged. If it falls anywhere out here, then we're going to say, yeah, it happens less than 5% of the time. And I'm going to say, yeah, that's too weird. So the chi-squared value is the value along that x-axis. Now, how do we find this p-value? Well, we go from the chi-squared value up and we shade in that area. That area is the probability of being at that point on the x-axis or farther. That's your p-value. And if your p-value is less than 5%, we've already decided ahead of time, we're going to reject our null and say, yeah, that's just too weird. Okay? Okay, so if you need to listen to that again, back up, listen to it again. So, looking at our coin, our scientific hypotheses are this. Our hypothesis is that the coin is rigged. It's rigged to land on heads more often. Our null hypothesis would be the coin is not rigged. It's got an equal probability of landing on heads or tails. So then how do we translate that to statistics? So our statistical hypothesis says, if the coin is rigged, our scientific hypothesis, if our scientific hypothesis is true, then we're assuming that the results that we got, that 81 and 19, comes from a rigged coin. That the differences we're seeing are because the coin is rigged. Versus our null statistical hypothesis is saying, I think those results, 81 and 19, are actually coming from a fair coin. In other words, this big difference that we see from our expectations is just due to chance. It's just noise. That's always your null hypothesis. And when we do statistics, we always start with the null, both the scientific null and the statistical null. So, and we're going to do this in class, but here's how you'd set it up. You'd say, all right, what's my claim to be tested? Well, the scientific claim is heads and tails, and we're starting with our null, right? This should say scientific null hypothesis. In fact, is the scientific null hypothesis says, I think heads and tails have an equal probability of landing face up in a fair coin. So my test, I'm going to flip the coin 100 times. That's my scientific experiment. And my prediction, my expected result, is that we should get a ratio of 1-to-1, 50-50, heads, tails. Okay, so then when we do flip it, we say, all right, I think that the results that I got were from a fair coin. So even though it said 81 and 19, I think it's just noise. That's my statistical null hypothesis. So the test that you run for statistics is you build a sampling distribution using your formula, your chi-squared. If I do it 100,000 times, what does that distribution look like? And your expected result is that the output value, whatever your chi-squared value is, for your observed results should fall well within the sampling distribution. It should be in that big part of the sampling distribution, not out in the tail. Okay? Excuse me. And then we run it. So let's say we run it. In this case, I'm going to plug in my values. I got 81 heads. I got 19 tails. I was expecting 50. So I get this chi-squared value of 38. Now you can see I'm using 50 here because that's how many flips I'm doing. You can imagine if I flip this 10,000 times, this number would get a lot bigger. So the x-axis is totally dependent on your sample size. That's why I didn't put any values along here, because It depends on your sample size. But let's say I plug this into my computer, I get a chi-squared value of 38.44 and I get a p-value of 0.03. This tells you where on the x-axis 38.44 falls. This is telling you that that score, we only get that score or something weirder than it 3% of the time. So where is it on here? Where is it where we only get it about 3% of the time? It's like way out here. It's probably right here, 38.44, where 3% of the time you get something that weird or weirder. And so we would reject our null and say, yeah, 81 to 19, that's pretty darn weird. I don't think it's a fair coin. I'm going to reject my null hypothesis that it's a fair coin, and I'm going to say the coin is rigged. Okay? So we're going to reject the null. The results are not just due to chance. It's far too bizarre. Okay, so let's go back to our original study. So we have this low sleep, high sleep. How do you decide how different that is? Well, let's run through our hypothesis, right? So the claim to be tested is that sleep has no effect. This is our scientific null hypothesis. Sleep has no effect. So we're going to set up our two groups. That's our scientific test. And our expected results should be that we should see no differences in exam scores between groups, right? So then statistically we say, I'm assuming that these exam scores are coming from two equally matched groups. Any difference I'm seeing is just due to chance. You get chance fluctuation in exam scores from semester to semester, and it has nothing to do with sleep. And I'm going to build a sampling distribution using my formula. Okay, now in this case, the formula is not going to be a chi-squared. We're going to use a t-test, for example. And a t-test, it's very similar, except that it can have positive or negative, right? So it can be lower than I expected, it can be higher than I expected. And so it looks like a normal bell curve. That most of the time, we're going to fall right in the middle where there's very few differences between the two classes, but sometimes we get bizarre differences just due to chance alone. And my expected result is that the output variable of my formula for my observed results should fall well within the sampling distribution. It should be in the big part and not out in the tails. Okay, now I'm not actually going to run that because I haven't actually figured out what my sample size is or anything. But going back to here, we would expect, when we ran it, we would expect a bell curve that had tails on both sides. And then we would do our little statistics and we'd figure out how often do I get exam scores that are this different when I've done nothing, when I've done no interventions in the class. And the way that we figure out these sampling distributions is we do it using computer modeling, saying if I were to take two groups of students that are totally identical in their scores and I would randomly pull two exam scores, how often would they be different by this 6%? And it would build a bell curve of how often you get a difference of 6%. And then it would tell you how likely is it that you get a 6% or weirder by chance alone. And if the p-value, which is the probability of getting something that weird or weirder, is smaller than 0.05, then we conclude that, eureka, our hypothesis is supported, that sleep does seem to matter. All right? So I'm going to post this so you can take a look at it as many times as you want. We will finish this up in class next time.